essentially the very elementary stuff that you might have forgotten. So it's just going to remind you of things you probably know. There will be a few things that you don't know about, but mostly it's stuff you do know about. This whole section is about probability, and start very simply with what is probability, some axioms of probability, and conditional probability, and then we'll move on to some standard distributions, standard discrete and continuous distributions that will show up later, particularly in queuing theory, and to some extent in game theory, but mostly in queuing theory. Poisson distribution, for example, shows up over and over again. And we'll end towards the next week with description of Bayesian networks, which is a way of talking about joint probability distributions over multiple variables. So it gets a bit more complicated, but it starts out pretty straightforward. All right, to begin with, so what is probability? There are many disputes about it, and in a few minutes I'll talk about different interpretations of probability. But from our perspective, what probability means is that we have some event that we're not really sure about. Okay, so for example, a classic example, you toss a die on a table, it has 6 sides, and you don't know which side is going to come facing up. So we cannot say this is going to happen, we don't know which number is going to show up. So since we don't have a definite answer, we can say, well, something is going to probably come up, and we can start attaching some numbers to it. So at some level, what we have with probability is that we have uncertainty. So probability is completely tied up with the mathematical representation of uncertainty. And so uncertainty is sort of a fact of life. We don't know what the stock market is going to do tomorrow. Apparently nobody else does either. So even the people on the stock market don't know what tomorrow is going to hold at this rate anyway. So uncertainty is a given, and one of the fundamental advances in mathematics which happened in the 16th century to 17th centuries was to recognize that it's possible to mathematically represent and capture uncertainty. So probability means uncertainty. How do you express uncertainty? In practical terms, what you're looking at is that you're building a system, okay? And in a system, what happens is normally you have some cause, and then you have some effect. And typically what we'd like to do is when you have a cause, you have a definite effect. You do this, something happens. You press a button, something happens. And it's exactly what you want it to happen. However, there are many cases where you don't know what's going to happen. You have some cause, and it may or may not have an effect. For example, I can lecture to you for an hour. At the end of it, the effect is, I don't know, you may not remember anything a month from now, or you may remember something a month from now. So the cause is there, the effect, we don't know. So what we do is to represent this uncertainty in terms of probability. Now, there are other ways of representing uncertainty, and they can have a big argument, and the AI people have been having an argument for many years. But what is the right way to represent uncertainty? We won't go into that, because all we're going to talk about is this particular approach, which is probability. Now, to make it more precise, what we say is this. We have that there is some cause, and the effect, instead of being this mushy cloud of, well, anything can happen, we be more scientific about it. What we say is that the effect is going to be an event, and that event can be enumerated in some fashion, either a finite or an infinite enumeration from a sample space. So what that means is that we are able to somehow enumerate or describe in some fashion the set of all possible events that can happen, or the effects that can happen, and then we'll say that the effect is one of these events that's chosen from the sample space. So again, we see the same kind of thing we saw last time with optimization. We're given a problem which is vague, and then we put on our scientific hat, and then we start building a model. And the way we build a model is we go and say, okay, what's the sample space? Okay. Once we start doing this, immediately things become more clearer. Instead of saying, well, I don't know what's going to happen, that's what a kindergartner would say. What you're going to say is, no, I don't know what's going to happen, but I know it's going to be one of these things, and then therefore I'm going to choose an event to be a member of the set called the sample space. Again, as I mentioned, the sample space can be infinite. All right. So let's take an example of this. I said one event, for example, was throwing a die. Now, it doesn't mean that this is a fair die. It's just a die with 6 sides. So the sample space is just 1, 2, 6. So it's a set of 6 elements, and we call and the event actually is die shows 1, for example. That is the event, and of course we can just shorten it to P1. That's the probability of this particular event. Okay, so if it's it's a fair die, its probability over here is 1/6, but it may not be a fair die. We don't really care. I just want to show you the notion of a sample space and an event. Now, similarly, we can say tomorrow it's going to rain or not rain, or it could be sunny or cloudy. Whatever, we can say that the event space it's cloudy and sunny, for example, as the sample space. And then we can say what's the probability that tomorrow is cloudy? That's an event, probably an event from the sample space. So we are basically focusing on this notion of events over here and sample spaces. Okay. Any questions about this so far? So the important thing to notice is when you're mathematically representing any problem, you have to immediately start thinking, okay, is this the right sample space? Am I leaving something out? Are these the right events? Okay, because if you ignore some events, ignore some part of the sample space, then obviously your model is already bad. Okay, you already made a mistake because you can't even associate a probability with something, okay, if you can't put it in your sample space. So you got to be careful about that. Okay, so once we have a certain definition of a sample space in the event, we are actually in a position to start formalizing it. And the way we do it is through the axioms of probability. And now it turns out that there are many different ways of expressing the axioms of probability. And I'm going to show you sort of 2 ways, more or less. And they all have to do with representing these events. What do you think about these events? Now, what does axiomatization mean? Okay, axiomatization is a process by which what we say is we make certain statements. We make about probabilities, and we expect that everybody intuitively understands what it means. Okay, there can be no dispute about these statements because intuitively it's obvious to you this is true. Okay, now if you disagree with it, well, then you're in a different axiomatic system. You say, okay, my axiom is different. Well, then that's fine. But as long as you're willing to accept these, then what the mathematical, the whole mathematical formalism says is, okay, you believe these, then through a series of theorems, and I can prove everything else from these axioms. In other words, the axioms are the bedrock upon which we build. And it can be shown that essentially everything in probability theory can be derived step by step from these 3 axioms. And where do these 3 axioms come from? It's intuition. Okay, so if you don't agree with them, then then it's not going to work. And the same thing comes, the initial process that started all this was in the Euclid, and where you had this axioms of geometry, which says only one line goes through 2 points, etc. 2 parallel lines don't intersect. These are the classical axioms, and then all of geometry can be derived from these axioms. In the same way, we want to derive everything about probability from these axioms. And it turns out it can be done. So these axioms are due to Kolmogorov, a famous Russian mathematician. And, well, I'll just state them for you, and you can see they are pretty obvious. The first one is that if there is, so we are going to use the thing that event is represented by the letter E. So essentially, and the probability of an event is denoted P of E. So that's pretty standard notation. So what we're saying is the first axiom says 0 is less than or equal to P of E less than or equal to 1. Okay. So what does this mean? It says that the probability is a number, it's a real number that lies in the range 0 to 1. Now we have some interpretation of these numbers 0 and 1. Okay. Now as far as the axioms are concerned, it doesn't matter what 0 and 1 mean. There's no meaning. It's just a number in the range 0 to 1. After that, you can mechanically do whatever you want to derive everything from it, and just but we have some meaning intuitively, and this let me start with this. A probability of 1 intuitively means this event is definitely going to happen. So you can say with probability 1, the sun will rise tomorrow. Okay, so that is a probability 1 event because that is definitely going to happen. You know, in your at least limited time scale over the next, you know, whatever 14, whatever next 2.5 billion years, you can say it's a probability 1 event. After that, the sun may disappear. But anyway, in that time horizon, that's a probability 1 event. On the other hand, what does probability 0 event mean? It means that almost surely it won't happen. Okay, it doesn't mean it surely won't happen, but it almost surely won't happen. Then there's a very kind of a subtle difference over here. Probability 0 event it's a sort of this event that you basically should not happen. Okay, but here's an example where I can show you it will happen. So let's take an interval of a line in the range, you know, I don't know, just 0, 1 for the sake of argument. And I'm going to pick a point at random from this real line. So I'm going to pick some point over here and just say, okay, that's my point that I chose. All right? Now, what is the probability of any particular point being chosen? Well, this line is of limited extension, you know, it's of 1 unit, but it has an infinite number of points. Okay, it has an infinite number of points. So obviously, any particular point being chosen has a probability of 0, right? However, if I add up all these 0 probabilities, I get a probability of 1 because I know for sure one of these points is going to get chosen. You see what I mean? So if I have an infinite set of things, I'm going to choose one from that set of infinite number of points. The probability of any particular point being chosen is 0. If I say, what's the probability that, you know, 0.5 is going to be chosen? It's 0, right? On the other hand, the sum of all these points is going to add up to 1. Yes?
I think you're talking about continuous.
Yeah.
Continuous. But what in the discrete?
In the discrete case, things are much easier. In the discrete case, probability of 0 means it's not going to happen. But in the continuous case, probability of 0 has a different interpretation, and it is an almost surely kind of event. And these kinds of paradoxes happen only in the continuous case. All right. So what we're saying over here is that we have this infinite, a sum over an infinite number of events, because what is the event? The sample space here is infinite. It's a set of all points. The event is a particular event being chosen. And we're saying the probability of this event, we'll now sort of mathematically define it to be having a probability of 0, and we'll interpret that 0 as being sort of almost surely, with the understanding that the probability over the whole range actually adds up to 1. So 0 has a kind of a funny meaning, whereas 1 is clear. Okay, so this is where you start getting into these arguments about what is the meaning of probability 0. Okay, does it mean it never happens? Well, so the way I like to think of it is that it is going to almost surely not happen. There are different approaches to explaining it, and you know, you can spend quite a bit of time on it, but I'm not going to. I'm just going to do that. Yes?
Don't you have the same problem with 1?
With 1?
It could also be viewed as an event that will almost surely happen.
Well, with 1, we don't have this problem of summation over infinite sample spaces where each event is 0 and the sum adds up to 1. So yeah, you can come up with interpretations where 1 also gets a bit funny.
Like for example, in the example you just gave,
yeah.
You asked what is the probability of picking an irrational number.
Yes.
That would be 1.
Yes.
That is probability of that. You might just pick a rational number as well. So
oh yeah, right. So I'm saying if you can take this argument and kind of turn it around and say, okay, I'm going to do that. But I just... yeah, okay. So both 0 and 1 have issues, but I have more trouble with 0 than I have with 1. Okay. In fact, with probability 1, you choose a transcendental number. Okay. That's because there are more transcendentals than there are even irrationals. So you get into more trouble that way. But in fact, you might choose 0.5 also. So you get into measure theory, and I don't want to get into measure theory because that's really beyond the scope. So we have to start, if you want to really understand it, you have to study measure theory, and I'm not. Okay, so what you think of as elementary and simple concepts of 0 and 1 actually have quite a bit more depth to them. That's just what I wanted to highlight over here. Nevertheless, from the perspective of the axiomatics, we don't care how that number was chosen. We're just going to say it's in the range 0 to 1. We don't care what it means either. Okay? As far as we're concerned, here is a real number in the range 0 to 1, and that's all I care about. And the axiomatic approach has that power that says we're able to ignore certain aspects of the problem because we're doing that. Okay. Let me just continue with the second axiom, which is somewhat easier. The second axiom says basically probability of sample space, which equals 1. So in other words, you've got to pick something in the sample space. This is nothing more than saying that the sample space is a union of all possible events. So, well, something is going to happen. Okay, that's what that means. Or you can, equivalently, you can say P true, where true is Boolean true, is 1, and P false equals 0. This is another way of stating P true and false. Or you might think of being definitions of true and false, whichever, again, what does true mean, what does false mean? Well, you can say, I can sort of mathematically state that from our perspective, true means it will happen, and therefore probability of true is 1 and probability of false is 0, but these turn out to be equivalent definitions. And so Kolmogorov second axiom is stated in one of these two different ways. And the third thing requires a little bit more definitional. So we need to define something. We define mutually exclusive events E1 and E2. Okay, so you're saying there are two events, E1 and E2, mutually exclusive. That means if E1 happens, E2 cannot happen. E2 happens, E1 cannot happen. So we cannot be in a situation where both E1 and E2 happen. Okay, so we're going to define that. And it's quite simple, to come up with E1 and E2. So basically, we can define E2 to be not E1. Then obviously, not E1 and E1 cannot happen at the same time. So it's quite easy to come up with these mutually exclusive events. And so what we say in the third axiom is that, so the definition of mutually exclusive is a probability of E1 and E2, which is also written as probability of E1 and E2, that's just some notation, equals 0. Okay. And I think in the notes there I said E1 EI EJ equals 0. What I really meant to say was probability EJ equals 0. So if you define this in this fashion, then we can make the following statements. So given a set of mutually exclusive events, I'll just call them E1, EI, EJ, etc. These are just some index. Then the probability of the union of these events, I equals 1 to infinity okay. So I guess I don't even need J over here. EI plus 1. All right. So I'm giving you a set of events, a potentially infinite number of events. Okay. I'm not saying these constitute the sample space. Okay. I'm not saying that. I'm just saying I have a set of events, and they're mutually exclusive. So if any one of them happens, then the other one cannot happen. All right. That's the definition of mutually exclusive. Now I'm saying, what is the probability of the union of these events? So in other words, either E1 happens, or E2 happens, or E3 happens, or E4 happens. If they're mutually exclusive, then I can represent that as a sum. So this allows us to introduce the notion of the summing of probabilities. And the summing of probabilities means that we are able to sum across elements that are mutually exclusive. Now, when I talked about the sample space earlier, I kind of said, well, these are the set of events that's going on. There is no reason for the sample space itself to have mutually exclusive events. Okay? It doesn't have to be mutually exclusive. You can have sample space where you can have cloudy, sunny, partly cloudy, whatever, any combination you want. That doesn't mean that the events in the sample space are mutually exclusive. But if you consider those elements in the sample space that are mutually exclusive, then the probability that any one of those happens, this basically means any one, or you can represent it as this way using logical notation. So instead of union, I could have the or notation. Then the probability of the or of any of these events is the sum of the probabilities. Okay, and that's it. Okay, so another way of representing this, by the way, is also commonly used, just basically probability of E1 or E2. And now I'm not saying they're mutually exclusive. They're just any two events is basically probability of E1 plus probability of E2 minus probability of E1 and E2. Okay, so you're saying if you have two events and they're not mutually exclusive, that's fine. We can add them up, and then you subtract away the common part. And the way to understand it is to use sort of this Venn diagram. You can say E1 corresponds to some space E2 is this. So if I do E1 plus E2, I'm getting this E1 and E2 twice. So if I subtract it out, of course, I'm going to get the overall union. So this one is obviously E1 and E2. So there's a fairly simple geometric explanation of why we need to do this. So E1 or E2 is a union, and to do this, and there's a set theoretic implementation, set theoretic interpretation, which is straightforward. We can think of E1 as constituting a certain sum of elementary events. That is these ones here. These are the elementary events over here, and then we take their union. We're going to remove those sort of sub-events or something that lie in this part over here. Okay, so then that kind of comes up as well. So there's a deep relationship between set theory and probability over here. Okay, so that is essentially the three axioms for Kolmogorov. Just to state them because they're raised. The first one basically says probability lies in the number. Probability of an event lies in the range 0, 1. The second one says that the probability of the entire sample space is 1, or probability of true is 1. The third one defines mutual exclusivity of events, and then we have a rule for how do we add mutually exclusive events. Sorry, how do we compute the probability of the union? It's just the sum. Okay, and these are the three things. Okay, let me stop and take a break here, and I guess I can put these two, and then we'll go on after that talk about the interpretations of actually came from China. Anyway, more on that later because I just finished reading that book. Okay, so what are the interpretations of probability? So when somebody says probability of event equals 0.25, what does it mean? And again, as I said, lots of work has been done, and I'm going to present sort of three approaches that people have used in order to give some semantics to it. And the first approach is what's called, counting arguments. And the counting arguments is essentially combinatorics. Okay, so I'm saying, okay, there are n ways of doing this, and this is equally likely ways. So if I divide it out, it's something. So for example, I have a die. I throw the die. So this is the classic thing: a die with 6 faces, and all of them are equally likely. That means the probability of any particular thing is 1/6, and that's it. It's a counting argument. And these counting arguments can be quite a bit more sophisticated. You're probably familiar with the balls and urns kind of thing, where you have some number of containers, often called urns for no particular reason, but I may have a certain number of elements in here, and I may choose a certain number. I put them back, and depending on how you choose these balls from these urns and what colors they have, these can get fairly complicated. And I will not go into them other than to remark that as long as you assume that it's equally probable to choose a particular ball from a particular urn, then all of the other math works out. But it all boils down to counting arguments. And so with these counting arguments, we can come up with mathematically precise, discrete probabilities, okay, like 1 over 6 or 1.25, 1 over 4, right? You can just do that. And that's fine. But that doesn't do everything for you. The second approach, which is called the frequentist approach, basically says that all probabilities actually arise from the limit, as limit sort of number of experiments tends to infinity, some metric on the experiment. Okay, so we have some experiment, we keep doing it, and we take the limit. So to take an example, to compare these two, let's say I have a coin and I flip it, right? It has a head or a tail, it's a fair coin. Now I say, what's the probability that it's going to be head or tail? Well, let's say, well, there are two possibilities, head or tail. We'll ignore that it lands on the edge. And so it's going to be 0.5, and that's a counting argument. There are two possibilities, each is equally likely, so it's 0.5. The frequentist approach would say, no, actually, how did you know there are only two possibilities? How do you know they're equally likely? You just kind of made it up, right? You actually didn't know that. What you've done, in some sense, is to do a series of experiments, and over a period of many experiments, you find that about half the time, you find that the metric, which is head or tails, is heads, and the other half of the time it's tail. So as you do an infinite number of experiments, or as you tend over here, this ratio will tend to 0.5. So what you really have is essentially the limiting value of some distribution. So if one were to actually plot sort of the number of flips over here, number of flips of the coin, and we're going to plot over here p head, what we can expect is that we have sort of 0.5 over here, and the number may actually oscillate, but eventually what we see is that the oscillations will die down, and we'll get this steady state where the limiting value is going to be 0.5. So that's called the frequentist approach, and their position as a philosophical approach is that there are no other probabilities other than frequentist probabilities, and everything can be viewed as in terms of an experiment. Okay. So we can take an example of this. By the way, this is the approach that's most often used in computer science, or in computer systems, networking systems. That's what is often used. So just to give you an example of this, what we'll do is, let's say I have a link, and then I have some source, and this source is sending packets on this link, and let's say they're TCP packets and UDP packets. And so if I look at it, there's some packet over here, and the header says TCP or UDP or other. Okay, so I want to ask this question. I pick a random packet out. I just kind of look at some random packet. It's coming in the middle or at the end, and I say, what type of packet is it? It's a perfectly reasonable thing to do. Obviously, there's some uncertainty because it could be TCP or UDP or something, and so we can enumerate the sample space. It's TCP or UDP or something else. So three elements, and I want to know what's the probability. Okay, so in the counting argument, well, there's no counting argument here. Because I can't really count anything per se. There's no mathematical object going on. But there's a very simple frequentist approach. And what that says is I'm going to take all the packets coming out. I'm going to put them in one of three bins. I'm going to put them in the TCP bin, and in the UDP bin, or in the other bin. And then I'm just going to put them over here. And then I'm going to, let's say, get 1 million packets. And let's say there are maybe 500,000 TCP packets and 450,000 UDP packets, and there's 50,000 other packets, and the sum is 1 million. Then I'll say, okay, probability of UDP, okay, is going to be basically 450,000 by 1 million, which is 0.45. Okay, that is a frequentist approach in the sense that we are saying million is large enough. Million is large enough, so things kind of get averaged out. That may not be true, right? For example, let's take the other end of the picture. I look at just 3 packets coming out. I get 3 packets, I put 1 here, and 2 end up here, and nothing is the other. Then I'm going to say probability UDP is 2/3, right? Because I got 3, I got 2. Well, you say, well, 3 is too small. 3 is too small. And then, well, how do you know 3 is too small? Well, it doesn't seem, intuitively doesn't seem enough. What you really can do is this. You can say, well, I'm going to start plotting this graph over here. On the x-axis, I'll have the number of packets, and the y-axis, I'll have PUDP, and I'll see whether it settles down. Okay. Now, we don't know if there's some kind of higher level time scale. All right. For example, it could be the case that somebody is using BitTorrent over TCP, and so it kind of bumps up the number of TCPs, and then in 2 months from now, in fact, the number of UDP is going to go up because some other application comes and UDP goes up. So at this point, we're in a big trouble because we don't know what infinity means, right? We're saying the limit as exponent tends to infinity is over here. So what's going to happen in the graph is that we have this oscillation all over the place, okay? And then it settles down. You say, oh, this is great. And you say, aha, I now have a steady state. Well, guess what? That wasn't a steady state. It suddenly is going to go like that. And maybe it reaches a steady state over here. Okay, because a certain traffic pattern changed. Or you could be measuring for an hour. Everything looks fine. And then, morning breaks. People start firing up the web browsers. More TCP comes up. And suddenly the probability of UDP goes up or goes down or whatever, right? So a fundamental issue in any kind of frequentist approach is that we cannot achieve infinity in real life. Okay? And so what we assume, or what you're forced to assume, essentially is that if you reach this period, it's called the stationary period, that the system is good enough, we measured enough. And one of the biggest problems when you do any kind of simulations or any kind of analysis or measurement study is, what does it mean for things to be stationary? And the general assumption we have here, and the general sort of working hypothesis, because we have to do something in real life, is we say, okay, this period looks long enough. We may draw a chart, show that it looks okay, and we hope, and we do this frequently, we do this enough times so that, things kind of settle down. But at the back of your mind, you need to be worried, because frequentist approach only, depends on this being infinity, and it depends on convergence of the probability value, and the probability value may never converge. There may be some dynamics such that the probability value never converges. So even this notion of 0.5 is suspect, because this looks like 0.5, but then at some point it may change, right? So you have to keep that in the back of your mind. But having said that, the frequentist approach, assuming convergence, can give you actual numbers that you can work with, and so this is what we use. Okay. Any questions about this? Yeah. So the question is, why can't, I'm repeating questions because somebody told me in the video, it was mine, I think, right? You can't hear the question. So the question is, why can't you use counting arguments over here? What counting argument can you use over here? I mean, the thing is that this is not like balls and urns. It's not a die. This is a link where stuff is coming out. I can look at the ratios, but that's a frequentist approach. Counting argument says, I have some mathematically decided prior that says, okay, if I have a die, it has 6 equal faces.
Yeah, but I mean, you don't have domain knowledge that you did have in the previous case, right? I mean, in the previous case, you assumed that the die was, or the coin was unbiased.
Yeah, so you're arguing on my side, okay? You're saying there is no domain knowledge. I'm saying, yeah, if you don't have domain knowledge, you're forced to use the frequentist approach. The counting argument approach works only when you have domain knowledge.
But if you had domain knowledge, even in this case, you could do something.
If you had domain knowledge, yeah. So if you're saying if you have domain knowledge, you could make the claim, yes. But in most practical networking situations, we do not have that kind of domain knowledge that allows us to say probability of TCP is 0.5 because that's the way it is. This is a traffic by its very nature is uncontrolled. We don't know what's going on. Okay. Any other questions over here? Okay. So the third approach, okay, so that was just an example of the frequentist approach. The third approach is what's called the subjective probability approach. Let me just erase this over here. Okay. So subjective approach. We have the same link, and I want to know the probability of UDP on that link. What do? I call up my friend who works for CAIDA, which is Center for Internet Dynamics at UC San Diego, and I say, hey, what's the probability of TCP? He says, I think it's 0.45. I said, great. I can put that in my paper. Okay, how does he know it's 0.45? He's an expert. That's his job. Okay, so the expert said so, so it's 0.45, and that's the end of that. Well, that sounds a bit flaky, but actually it's true. You go to a horse track and you place a bet on a horse, and you say, I think with 0.8 probability that horse is going to win. Or maybe you don't do it, but some person might who bets on horses. How do they know? The thing is, there are way too many factors influencing that horse winning. It could be that the horse is young, it has a long stride length, it ate well, it slept well last night, the wind is not against it. Maybe the jockey is a special jockey. Maybe on the side of the racetrack there's some flowers planted, and they make the horse give extra energy because it doesn't like the smell, so it goes faster. Who knows, right? There's so many factors, it's impossible to decide. But the expert knows it's 0.8. How do we know the expert knows it's 0.8? We know that because we can do the following experiment. You can say, all right, if this horse wins, if this horse loses, you're going to get no money. If the horse wins, I'm going to give you $1. Will you bet on it? You say, oh no, you need to give me more, okay? Because expectation. So let's take the following bet. If you win, you get $1.25. If you lose, you get nothing, all right? And if your probability of win is 0.8, what will happen is this will be the lowest bet that you'll accept, okay? So 0.8 as 1.25 turns out to be $1. So basically, you have to bet $1, okay? So if you bet $1 and your probability of win is 0.8 and you get payoff of $1.25, then you're coming out even. You're not losing any money, all right? And if you think the probability of win is 0.9, this actually is a very good bet. So you start with the high winnings. Okay, you start with, I'm going to give you $2. Will you bet? Yeah, sure, no problem, because I'm going to get $1.60 back, and you only put in $1. I'm making money. You keep lowering it and lowering it. At 125, guy says, well, if you go below, I'm not going to bet. But at that point, you know that his probability of winning is 0.8. So you can sort of elicit the probability, the subjective probability, by doing this experiment. And that's sort of the hypothetical experiment that people do. So in the same way, when I call up my friend and say, what's the probability TCP? I'll say, okay, I'll tell you what, you give me $1, and if it's a TCP packet, I'll give you back some amount of money, and if you don't, you lose it, okay? And now, tell me at what point you're going to be willing to make this bet. And exactly at the point where they say, look, I'm not going to take this bet anymore, is the point of, you can determine the probability. So there are some methods to estimate these probabilities, and that's what has been the subjective probability. Okay. Any questions about this? Yeah.
Distributions, like you want to mention, do they fall into the frequentist category, or
okay.
Place that?
So the question was, how do distributions fall? Okay. Right now we're talking about events and sample spaces. I haven't told you about random variables. So the probability associated with the random variable is drawn from the underlying set of events. Okay, because random variable is sort of a function on the event space. Now each event has its own underlying approach for determining the probability, and the random variable acquires that. So when we talk about random variables in just a minute, well, I guess, yeah, a little bit later we'll talk about that. Okay, so just to sum up, when you see something that says probability of event is this, there are actually 3 different ways of coming up with this. One is a counting argument, sort of based on physics. A second one is based on a frequentist approach, which is the approach that we will mostly use in systems design. And a subjective approach, which is used primarily in game theory, because we have these outcomes and expectations, and we really don't know much about it. The nice thing about all this is, from the perspective of the axiomatic theory, we don't care. Okay, as long as we have these probabilities assigned in a way consistent with the axioms, it doesn't really matter how we got them. So that's nice. Okay, so let me now move on to conditional probability, and a fun example of that. So that's interpretations. We know about conditional probability. Are there any questions about this? Yeah. The third approach has some elements for the Bayesian approach. The Bayesian approach, we'll talk about that later, actually, in the last class. When we talk about Bayesian networks, there's a notion of a prior in Bayesian approaches. And in the prior, where did that come from is the question, right? And that comes from typically the subjective approach. But one could argue that prior comes from frequentist as well. Okay, so again, there are many very deep and subtle arguments that I don't even fully understand that I'm not going to go into. Yeah, but that's not the Bayesian approach. Bayesian approach means something slightly different. Okay, so let's talk about conditional probability. So very simple. Conditional probability has to do with two events. I have an event E and I have an event F. Okay, and F happens after E. Just like in the alphabet, F comes after E. So I have event E and event F. And I ask the following question. Event E has happened. All right, event E has happened. Now, does that affect anything about event F? Okay, that's basically it. So I've told you that E has already happened. It's in the past. Now, does that change anything about event F? Okay, so we'll take an example like this. For example, one might say that the event E is that, it's cloudy. Okay, the E could be cloudy or sunny. And F is rain. Okay, so rain today, to be more precise. It's cloudy or sunny today. Now, one can say, all right, tell me the probability is going to rain today. Oh, its probability is, whatever, 0.5, based because I'm an expert. And then I say, oh, wait a minute, I just looked outside the window and I see that it's sunny. What's the probability? Okay, maybe you say, oh, if it's sunny, then my expectation, my probability has changed. It's not 0.5 anymore, it's now down to 0.1. All right? So either E affects F or not. If E does not affect F, okay, then E and F are independent. Now, independent is not the same as mutually exclusive. That's a different thing. Mutually exclusive means either E happens or F happens, but not both. But we're not talking about that. We're talking about E happening and the next stage, F happening. It's time series, not simultaneity. If E does not affect F, then E and F are independent. Otherwise, they are dependent. And we introduce a new notation, and we introduce this notation which is probability of F given E, where the vertical bar is written as given. So what's the probability of F given E? All right. So either it's the same, it's probability of F, which was before, or otherwise it's defined to be basically probability of F and E over P E. Okay, let me make sure I got this. Okay, yeah. So what we're saying, this is the definition. By definition, P F given E is defined to be P of F and E given P E. Okay, that's just the notation that we use for this particular ratio. And what we're saying over here, sort of intuitively, is like this. We have the universe of all possibilities open to us. Now, what we do is we know that E has happened. Okay, we know that E has happened. So what we're going to do is I'm going to remove all those events that are inconsistent with E happening. All right. So, for example, before I knew that it was sunny outside, the universe of all possible events included sunny outside, cloudy outside, hailstorm, snowstorm outside. All of these events are possible. All right, and I have some idea of whether it's rain is going to happen given it's cloudy, rain is going to happen being sunny, rain is going to happen being etc. Each of these things. Now what happens is I've been given some information which is it is sunny outside, so I'm going to remove all of those events and restrict the sample space. And so when we do that, it turns out that the probability of F given E comes out from this particular value over here. And just to get our analysis and the axiomatic approach to work, we have to define it in that particular fashion, and also you can justify it yourself independently. Now, so I guess I want to emphasize that E and F is not equal to F given E, okay? Or maybe I should just call it F and E is not the same as F given E. This is a confusion that many people make. F and E means that F happened and E happened. Okay, so this is after the fact. F has happened and E has happened. Both things have happened, whereas F given E means E has happened and we don't know anything about F yet. Okay, so that's that's why we have F. What's the probability of F given E as opposed to F and E? Okay, so or another way of putting it is that F and E is in the original sample space. Whereas F given E is in a reduced sample space. And the easiest way to explain this is through an example, so I'm going to actually just go directly and do an example that's in the lecture notes. And I think when you see that, hopefully you will be able to better understand the difference between these two things. Okay, so what we're going to do is that we have the following thing. We have some source, we have some link, and I've already told you that probability of TCP is 0.5 and probability of UDP is 0.45. Okay, this is already there because that's what we did in the first example. So what I'm going to do is this. I tell you that 20% of UDP packets have length 52 bytes. Okay, that's just a statement I made because I looked at all the UDP packets, just the UDP packets, and I measured their lengths. It turns out 20% have a length of 52 bytes, which means we can, in the frequentist approach, we can say probability that length equals 52, okay, conditional on packet is UDP, equals 20%. Okay, so now we are seeing how we use these conditional probabilities. Okay, so what we've done is we've taken the stream and just if it's not a UDP packet, we ignore it. All right. So what we've done is we've conditioned on UDP. Okay, so conditioned on UDP, then the length is 52 is 20%. Is actually, so this is 0.2. Okay, so now you see how we use the conditional probability, and now we can actually use the following thing. If you see this equation over here, PF given E, and this is often written as PFE over PE. What this means is that PFE is nothing more than PF given E PE. Okay, so probability of UDP and 52, which is the event that its length 52 bytes, is nothing more than probability 52 given UDP times P UDP. All right, and now I can just plug these values in. This is 0.2, and this is 0.45. So this gives me basically 0.225 as a probability. Oh, sorry, what am I doing? Not 0.5, 0.09. As a probability that it's UDP and 52. Okay? So just look at these two things over here. One is the probability of UDP and 52. Okay? This is on the sample space of all packets. If you look at all packets and I say, okay, what fraction of these are UDP and 52? It's only 9%. But if I ask you what fraction of these are 52 bytes long, if I tell you they're already UDP packets, well, that's 20%. So what's happening is UDP packets are sort of richer in 52 bytes. Okay, okay. So I'm sorry, they're not really. They're only 20%. Okay, there's 80% probability of them being not 52 bytes. So about half of the packets are UDP, and about 20% of those are 52 bytes. So overall, it's UDP and 52 is only 0.09. But that doesn't tell me about how many 52-byte packets there are overall. Okay, I'm just looking at the event UDP and 52. Okay, and so we can use this formula over here to compute that, and that's 0.09. Okay, so just to kind of summarize over here, here we have two events. Event E is that it's UDP, F it's 52 bytes. We look at UDP and 52. It's probability 52 given UDP, so that's F given E times P UDP. It's probability E, and that gives me P of F and E, which is 0.09. Okay, so if I pick a packet and say, is it UDP and 52? 0.09, 9% of the time, it will be true. Okay. Any questions about this so far? Okay, I'm in danger of putting all of you to sleep, but I'm going to write one more. I'm actually, well, maybe I should just do the, yeah, I'll do a short break, and then we can go into this Monty Hall, I guess. Both are not dependent, they're both happening at the same time. What is the probability that these two events happen at the same time? That is, it is UDP and the length is 52.
But you use this formula, and it's we're only using it when the two events are dependent, right?
That's correct. It is dependent. Yeah, the fact that it is of length 52 depends on it being UDP. Okay, they're not independent events.
But can TCP be 52?
TCP can be 52 too. I'll come back to that after the break. Yeah, I could see many people going off to sleep. So yes, TCP could be 52 too as well, right? So if I tell you it's TCP, I have a different probability of being 52. Tell you it's UDP, different probability of being 52. And we'll look at we'll talk about the generalized. I'll come to that when we talk to Bayes' rule. So there is a famous problem called the Monty Hall problem, which has to do with conditional probability, and I put it in here because it's kind of fun, and it also explains quite a bit about conditional probability. Some of you will understand it right away. Most of you will not. That's okay. Go back and read it later. So what's the problem? So Monty Hall, apparently, I never watched this, was a game show host on TV, so he had a game. And there were in this game, there are 3 doors that you look at. And behind one door is a car. And that's my car. And behind 2 of them are goats. And I'll try to draw a goat. That's a goat. And that's another goat. I'll draw the beard there. Okay. You like cars better than goats. I don't know why, but that's the story. And here you are, standing behind the podium. And your 3 doors marked 1, 2, and 3. And you can't see what's behind them. And if you pick door 1, you get the car. If you pick door 2, you get the goat. If you pick door 3, you get the goat. Okay? So chances are 1 out of 3 that you'll get the car. Okay? So what happens is you're asked to pick a door. And without loss of generality, you pick door 1. All right? Now what Monty Hall does is he says, look, I'm going to open another door, and I'm going to show you what's behind it. Okay, so he opens another door. Without loss of generality, he opens door 2, and he shows you there's a goat. So you can now see that there is a goat over here. Then he says, do you want to change your mind? Do you want to switch? Or do you want to stay behind? Do you want to keep door 1, or do you want to switch to door 3? Okay. So what should you do? Should you switch or not? That's the Monty Hall problem. So does anybody have any suggestions whether you should switch or not? Sorry? You should switch. Why? You're saying it doesn't matter, okay. And Chan, you say you should switch because you read the lecture notes. No, why should you switch?
Because if you switch, the chance of getting a car is 50%. But if you don't switch, the chance is only 33%.
Okay, so you're saying if you switch, the probability of getting a car is 50%, and if you don't switch, the probability is 33%. They don't add up to 1, so that's actually wrong. Because they're going to get it or not get it. So they have to at least add up to 1. You're violating the axioms of probability, so your answer is wrong. Anybody else want to try?
All that he's done is made you question yourself.
Okay, all that he's done is made the question himself. Okay, you're also wrong, but I'll explain to you why. That's actually a more deeper problem. So anyway, as I said, most of you will. Okay, go ahead. Question. Yeah.
The probability of winning doubles, right? Because it's 1/3 originally, and now there's just
Right. So the answer is, he says, well, it's better to switch. You double your options by switching. And so let me explain that answer, because that is in fact the correct answer. The way it works is like this. Initially, all of them have probability mass 1/3 behind them. Think of that as being a 1/3, 1/3, 1/3 behind them. Okay? So that's the initial sample space, door 1, door 2, door 3. You can actually write it like this. Door 1, door 2, door 3, and they each have 1/3, 1/3, 1/3 behind them. Now, what happens is that you picked door 1. Let's say you picked this over here. And now what's going to happen is like this. Okay, it doesn't matter where the goats are and where the cars are. You can be sure of one thing. Monty Hall will never open a door with a car behind it. Okay, he's never going to do that for sure, right? So he's going to pick either door 2 or door 3, but whichever one he picks is for sure the door with the goat. No, he knows where the goat is, right? You may have picked the car or not. He knows where the goat is. So he has reduced the probability of this down to 0 because he opens, let's say, door 3 and he reveals a goat to you. Okay? Now the probability has gone away. Now let's consider these two situations over here, this or this, right? He's not going to open this door for sure, okay? So you actually got no information about this at all because you picked this. He's never going to do anything over here. So this stays at 1/3, which means that this other third must come here to get 2/3, and so if you switch, you will get 2/3. Okay? So what's going on is that the original sample space was this, and the reduced sample space is just this. The sum of the probabilities in the reduced sample space have to add up to 1. This door 1, since it is never going to be revealed to you, cannot change. It's independent. Whether he reveals this or this, it doesn't matter what's going on over here. Therefore, it comes over here. Okay, so it's a very counterintuitive kind of thing. That's why I said most people don't get it. The other way of explaining this is that by choosing which door to open, 2 or 3, private information is being revealed. This is private information that Monty Hall has, which is, where is the car? He's always going to pick that door behind which there's a goat. So by doing that, you can think of that as that collapses the probability distribution over there and moves it over to the other door, and that's what's happening over here. Moving the probability mass over here, and that makes it more likely, in fact twice as likely, so you should always switch. Okay, this just to illustrate the fact that conditional probability seems easy until you start thinking about it some more, and you realize that you have to look at it in the reduced sample space. Once you do that, then it becomes pretty straightforward. Yes?
If you remove the statement that he's always going to pick door with a goat, does that change the
Yes, it does. Because the thing is, if he reveals, if you say he reveals, he doesn't reveal, sorry, he may reveal the car by opening the door, right? Then the problem, actually the problem becomes trivial then, right? He opens the car, well, what's the point?
He could have picked any door and he picks one with a goat.
If he picks the one, if he picks the one,
He picks the one with a goat.
I'm sorry, he might pick the one with the goat or not.
So if he randomly picks one and it turns out to be a goat,
Yeah.
he didn't have, for example, if he didn't have advanced information, does that change?
Yes, see, then the structure of the problem becomes difficult because he has to pick all 3 equally likely. But then he's going to pick the door that you change, and you can't say, can you switch? The problem doesn't even exist anymore, right? This problem exists only because of this particular structure that's being followed. And if he picks everything equally likely, then it's a different problem, and then you have to look at the sample space again. But in fact, sample space is going to reduce down to 2 doors. You have to see how the probability mass moves over. Okay. All right, so if you don't believe this, in fact, on Wikipedia, there is a tree showing all possible accounting arguments showing all possible decisions, and in fact there's a nice Java animation where you can pick doors and you can see your winnings or losings and so on, and I'll ask you to try it. It's kind of a fun thing to do, and you do get a goat even bleating in some. There's several websites doing this. Some of them the goat even shows up and pops right out. So it's kind of fun. Okay, so that's the Monty Hall problem, and I really encourage you to go back and read that material in the notes because it's a bit more complicated than it appears. Okay, so now we come to a famous rule called Bayes' rule. Actually, are there any questions about this over here? Or? Okay, I think I would prefer to handle questions this next week after, or on Thursday after you had a chance to think through it, because it's a bit. Okay, so let's look at this. There's a famous rule called Bayes' rule. This is not the same as Bayesian network. It's just a rule. And well, what is Bayes' rule? We know that P, E, and F is given by P, F given E, P, E, right? But in fact, you can also write this as P, by just interchanging E and F, E given F, P, F, right? It's just, flipping the variables around, which means that P, E given F is nothing more than P, F given E, P, E over P, F. Okay, I'm just transposing this to the denominator over there. That's all I'm doing. Okay, so this is what's called Bayes' rule. Again, it looks pretty trivial, right? It's pretty trivial. I'm just saying, okay, I have if and D. I kind of manipulate it algebraically, and I get this. Okay, so let's understand a little bit more. What's going on is that we have the event E, and then at time t1 and the t1 plus whatever delta, we have event F. So F is sort of E is the cause, F is the consequence, the cause and effect. What we're saying is that I want to know what is the cause given the effect. Okay, I'm changing the direction of causality. Okay, another way of thinking about it is, somebody says if there's a fire, there's a probability of 0.4 there's going to be smoke. Okay, then I say, okay, there is smoke. What's the probability there was a fire? Okay, so given the effect, what is the probability of a cause? This is why this is such an important equation, because it allows us to reason about the probability of causes from observed effects. And this is very, very widely used in AI. What happens there is we say, okay, something happened, then we go back and say, what is the probability that was due to this? Okay, or somebody fell sick, you're a doctor, and you see somebody comes in, they have a sore throat, that's the effect. Then you say, okay, what's the probability that was because of meningitis or because of viral infection or whatever? And so this is essentially diagnosis. Given the effect, what's the probability of the cause? Okay, and we have to, it just comes out from this. Basically, we plug this equation in, and it's not a particularly complicated equation, and we can reason about what the cause could be. Okay, I'm going to kind of give you I'm going to continue with that UDP, TCP example over here. And to do that, first I'm going to kind of remind you about something. So I had this link, and I had this thing called P, probability to TCP was 0.45, sorry, it was 0.5. And the probability of UDP was 0.45. Probability of other was 0.05. And then I also said that 20% of UDP packets are 50. So I said P52 given UDP was 0.2. And let's also assume, or I'll just tell you, and where is it? I have to look up that number, that P52 given TCP, that means what fraction of TCP of 52 bytes? Let's just say that it is 0.9. So 90% of TCP packets are 52 bytes long. I just had that measurement as well. So now what I'm going to do is this. I'm going to say, I'm going to ask you the question, if a packet, so I sample a packet, okay, it's 52 bytes long. Okay, what is the probability it's UDP? Okay, so that's what I want to find out. What's the probability that's UDP given that it's 52 bytes long? So this is the effect, is that it's 52 bytes long, and the cause, one of the causes is UDP. The other cause, of course, is TCP, right? Now, I guess I need to also say that probability 52 given other, let's say, is 0. Okay, if it's any of the others, you can know for sure it's not a 52-byte packet. So what we need for this computation over here is this. Okay, so let's just go back to the formula over here. So probability that it's UDP given 52, okay, is nothing more than probability of UDP and 52. Okay, that's P. F. Sorry, other way around. F given EPE. So it's probability of 52 given UDP times P UDP over P 52. Okay, that's the formula. Now the thing is, what is P 52? Okay, now I have P TCP and P 52 given TCP, P UDP, and so obviously P 52 can be written like this. P 52 is what? P UDP. Let me actually write this like this. P 52 is nothing more than P 52, okay, and P1, right? Because it's true, it's just nothing more than P 52 times P UDP plus P TCP plus P other, right? Because it's either UDP or TCP or other. That three of them cover the sample space. So P1 is these three things. And so this is nothing more than P52, P UDP plus P52, P TCP plus P52, P other, right? And now I can just multiply these out. This last term is 0 because P, wait a minute, actually, oh geez, I got this wrong. I have to put the conditional, I'm sorry. It's a good thing it's a whiteboard. What I want to do is P 52 times P 52 given UDP, because that's how I get the joint, plus P 52 times P 52 given TCP plus P 52 times P 52 given other. Oh gosh, no. Okay, it's getting late. This is, yeah, UDP, sorry. Okay, now we're finally making some progress here. It's a bad thing it's being videotaped. Sorry, so the probability of AB, I'm just using this over here. P of AB is nothing more than P B given A PA. So I'm just saying that conditional it's UDP. Okay, I want to know that it's 52 given is UDP, multiply the P UDP, right? Plus conditional that's 52 given TCP times P TCP, plus conditional that it's other, it's 52 given is other, P other. Obviously, if I multiply these three out, I'll get P 52. And so I can multiply these out over here to be, so P UDP is 0.45 times P 52 given UDP is this, so it's 0.2 plus 0.5, and P 52 given TCP is 0.9 plus 0. And this one comes out to be, I believe, 0.54. Where did I put that? Yeah, 0.54. So that's the number we need, okay? And we can plug that into here. So what's P 52 given UDP? Well, that one again is 0.2 times P UDP is 0.45 over 0.54. And this turns out to be 0.78, if I'm not mistaken. No, not point. UDP given 52. Nope. 0.167. I remember. Okay. All right. So sorry about that. I got a bit confused over here. So let's go back and see what I'm doing over here. These are the parameters that are sort of input parameters. This is measured This is measured, P UDP, P TCP, P other. This is just what fraction on the link have these parameters. Right? The second thing I told you was that if it's UDP, then it's 52 bytes long with probability 0.2, and similarly for these other things. Now I have enough information, so what I want to show you here, that if I sample a packet and I see it's 52 bytes long, I can answer the opposite thing. I've seen it's 52. Where does it come from? Is it a UDP, is it TCP, or other? Okay, so let's figure it out. From Bayes' rule, we see the probability that it's UDP given 52. So this is over here, E given F is nothing more than F given E times P E divided by PF. All right, just using the same label over here. The thing is, I didn't know what P52 was. Okay, I didn't know what P52 was. I only had these things, P52 given UDP, PUDP, etc. What I'm saying over here is that we know that probability of AB is P B given A, PA, right? Basically because by the definition of P given A, I remember I said that P B given A is defined to be P AB over P A, right? By the definition that I showed earlier. So I can just multiply this, so I can multiply this out, P A times P given A is P A B, because I want to know the joint probability UDP and 52, right? So P52 and 1 is P52 and this or this or this, which is P52 and PUDP, or P52 and TCP, and so on. And that comes out to be this thing, UDP times this. This comes from this equation over here. And when I plug these values in, I get 0.54. I can now go back here, plug this in here, and I get 0.167. So that means that if I see a packet and I see the measurement and it's 52 bytes with probability 0.167, it is a UDP packet. Okay. So intuitively what's going on is that I have the set of all possible types and I have all possible lengths, but once I tell you it's 52, I can work back through the chain of causation to essentially figure out what is the probability it's UDP. And this sort of illustrates two things. The first thing it illustrates is the utility of Bayes' rule. The utility of Bayes' rule in that we can infer from effects back to causes. So we are able to infer from the length back to the cause, in this case is UDP, and we can attribute, in some sense, that it was 52 because of UDP. This is a degree of attribution, as they say, to the cause over there. The second thing is what I've done over here is actually derived through an example, the generalization of Bayes' rule, which is nothing more than over here I said PF. It can be represented as, so we can write this. I'm going to write down the general Bayes' rule, and you'll see it's pretty much what I applied over there. If we can write E in terms of, so basically you can write this as this, P F given EI, where EI is the ith event, PEI over sum I equals 1 to n, P F given EI, PEI. Okay? So if you see what's going on over here, what factor shows up on top? P52 given UDP, PUDP, and that shows up over here as well. This is the same as the numerator. What we're doing over here is that, in some sense, this product of 52 given UDP, PUDP, okay, is sort of the fraction of time that you have 52 due to UDP divided by the fraction of time it's 52 due to anything else, which are the denominators, and that's what shows up over here. So this is the generalized Bayes' rule, and the derivation is exactly this. You say it's and P1, then you expand it out, you do this over here, and you can just prove this generalized Bayes' rule. Essentially, it's a very, very straightforward derivation. So what can we do now with this? What we can do is that we can look at these individual pieces, that is, the probability of having some effect due to each cause, some effect 52 due to each of these causes, and the intrinsic underlying probabilities of things happening, and then we can now work backwards. We can say, okay, I saw this effect. Okay, now I can tell you which cause it could have been. All right, and this is very, very useful in medical diagnostics, because we can say probability of meningitis is something, probability of viral infection is something, probability of bacterial infection is something, and then probability of sore throat given meningitis is this, probability of sore throat given this is this. You can work it back, and then we plug it away. We say, okay, I see a sore throat, what's the probable cause? I can tell you the most probable cause. So all these medical reasoning systems essentially use this kind of thing over here. Same thing shows up in medical tests. So let's say that probability that you have some blood test and it comes up bad. You can look at basically what's the probability of having certain underlying diseases, and then what's the probability of having that test show positive given each of these causes. Then you say, okay, your test shows your glucose level is high. You can work back and say it's most likely you have diabetes. Okay, and we can figure that out over here. So that pretty much is generalized Bayes rule. And I'm going to, there's an example in the notes you should probably look at. But are there any questions about this over here? Okay, so it's, you start over here and you plug away and then you kind of get this, and that's a generalized Bayes rule. And the application of generalized Bayes rule is in fact in Bayesian networks. And now actually I'm in a position to answer your question. What's happening in Bayes' rule is that we have some underlying assumption about the likelihood of these things going on over here. We have some underlying assumptions about these conditionals. Given these, we can then reason backwards about the effect and the cause. So where did these come from, right? In the frequentist approach, you can say, well, these came from measurements. But these conditionals, it's not clear where these came from, etc. So in the Bayesian view of the world, experts sort of give you these priors, and then you can invert things around. So anyway, I think I should probably stop here because I have a meeting at 1. I have to run to. So yeah, so we'll stop for now, and we'll continue. I'm up to page 8 in the lecture notes.